morning. I am Mr. DHAKSHUNHAAMOORTHY, AP-AIML department. Today's topic is eligibility traces in the subject 21 AM 903 reinforcement learning under the unit 3 temporal difference learning. Eligibility traces. Eligibility traces is a kind of mathematical trick that improves the performance of temporal difference methods in reinforcement learning. Benefits of eligibility traces: provide a way of implementing Monte Carlo method in online fashion, does not wait for the episode to finish, and on problem without episodes. Provide an arithmetic mechanism that uses a short-term memory vector computational efficiency by storing a single vector memory instead of a list of future vectors. Learning is done continually rather than the waiting results at the end of the episode. Eligibility traces forward view of TD lambda. Backups can be done not just toward any n-step return but toward any average of n-step returns. For example, backup can be done toward a return that is half of 2-step return and half of 4-step return. That is mathematically written RT average equal to half of RT of 2, that is 2-step return, plus half of RT of 4 raised to 4, that means 4-step return. Any set of returns can be averaged in this way, even an infinite state, as long as the weights on the component returns are positive and sum to 1. The overall return possesses an error reduction property similar to that of the individual n-step returns and thus can be used to construct backups with the guaranteed convergence properties. Averaging produces a substantial new range of algorithms. For example, one could average 1-step and infinite step backups to obtain another way of interrelating TD and Monte Carlo methods. In principle, one could even average experience-based backups with DP backups to get a simple combination of experience-based and model-based methods. A backup that averages simpler component backups in this way is called a complex backup. The backup diagram for complex backup consists of the backup diagrams for each of the component backups with the horizontal line above them and the weighting fractions below. For example, the complex backups mentioned above, mixing half of 2-step backup and the half of 4-step backup as the diagram. In the figure 7.3, the backup diagram for TD function, if lambda is 0, then the overall backup reduces to its first component. The 1-step TD backup, where if the lambda equal to 1, then the overall backup reduces to its last component, the Monte Carlo backup. Here in the first backup diagram, we can able to see half of the 2-step reward and half of the 4-step reward we are averaging. Here it goes to, if it is the diagram goes to infinite step also, we can see for the 1-step 1 minus lambda and 2-step 1 minus lambda into lambda, 3-step 1 minus lambda into lambda square, and goes on lambda power capital T minus small t minus 1. The sum should be equal to 1. TD lambda algorithm can be understood as one particular way of averaging n-step backups. The average contains all n-step backups, each weighted proportional to lambda power n minus 1, where lambda lies between 0 and 1. Normalization factor of 1 minus lambda ensures that the weight sums to 1. The resulting backup is toward a return called the lambda return, defined in the mathematical format RT raised to lambda is equal to normalization factor 1 minus lambda into summation of n is equal to 1 to infinite lambda power n minus 1 into RT power n. This can be rewritten as RT lambda is equal to 1 minus lambda into summation of n is equal to 1 to capital T minus small t minus 1. Here lambda power n minus 1 and RT power n, and summation with the lambda power capital T small t minus 1 into RT. The equation makes it clearer what happens when lambda is equal to 1. In this case, the main sum goes to 0. Yes, in this graph itself we can able to see the main sum, it goes to 0. Drastically the graph is going down, goes to 0, and the remaining term reduces to conventional written RT alone. Thus, for lambda equal to 1, backing up according to the lambda written is same as the Monte Carlo algorithm that we called a constant alpha in this previous chapter. On the other hand, if the lambda equal to 0, then the lambda written reduces to thus one step written. Thus the lambda equal to 0, the backing up according to the lambda written is the same as the one step TD method, TD of 0. The mathematical equation del Vt of St equal to learning rate alpha into reward RT raised to lambda minus Vt of St. The approach that we have been taking so far is what we call the theoretical or the forward view of learning algorithm. For each state visited, we look forward in time. We are looking forward in time to all the features. So in the diagram itself, the particular observation is taken from starting state, and we are looking forward in time. So that reward for the first state is RT plus 1, reward for the second state is RT plus 2, RT plus 3, and so on. For each visited, we look forward in time to all the future rewards and decide how best to combine them. We might imagine ourselves riding the stream of states, looking forward from each state to determine its update as suggested by the figure 7.5. After looking forward from and updating one state, we move on to the next and never have to work with the preceding state again. For future states, on other hand, are viewed and processed repeatedly once from each vantage point preceding them. Backward view of TD lambda. In the previous section, we presented the forward or theoretical view of the tabular TD lambda algorithm as the way of mixing backups that parametrically shifts from TD method to Monte Carlo method. In this section, we instead define TD lambda mechanistically, and in the next section, we show this mechanism correctly implements for forward view. The mechanistic or backward view of TD lambda is useful because it is simple conceptually and computationally. In particular, forward view itself, it is not directly implementable because it is causal, using at each step knowledge of what will happen many steps later. The backward view provides a causal incremental mechanism for approximating the forward view, and in the offline case for achieving it exactly. In the backward view of TD lambda, there is an additional memory variable associated with the state. It is eligibility trace, ET. Eligibility trace for state S at the time T is denoted E of T, ET of S belongs to R plus. On each step, the eligibility trace for all states decay by gamma lambda, and the eligibility trace for one state visited on the step is incremented by 1. For all non-terminal states S, where gamma is discount rate and lambda is the parameter introduced in the previous section, henceforth we refer to lambda as the trace decay parameter. This kind of eligibility trace is called an accumulating trace because it is accumulates each time the state is visited, then fades away gradually when the state is not visited, as the illustrated below. Here in the diagram itself we can see uh, four step of response we are getting when the state is visited. When state is not visited, the uh, response is decaying slowly. Here accumulating eligibility trace the time of visit to a state. Here eligibility trace E of t et of s is equal to gamma lambda et minus 1 of s if s is not equal to st, gamma lambda et minus 1 of s plus 1 if s is equal to st. At any time the traces record which is states have recently been visited, where recently is defined in terms of gamma lambda, the traces are said to indicate the degree to which each state is eligible for undergoing learning changes should a reinforcing event occur. The reinforcing events we are concerned with are the moment by moment on one step TD errors. For example, TD error for state value prediction is del t equal to reward RT plus 1 plus gamma into VT of ST plus 1 minus VT of ST. In backward view of TD lambda, the global TD error signal triggers proportional updates to all recently visited states as signaled by their non-zero states. Del Vt of s is equal to alpha del t et of s for all s belongs to capital S. As always, these increments could be done on each step to form an online algorithm or saved until end of the episode to produce an offline algorithm. In either case, equations provide the mechanistic definition of the TD lambda algorithm. A complete algorithm for online TD lambda is given below. Initialize V of s arbitrarily and E of s is equal to 0 for all s belongs to capital S. Repeat this step for each new episode. This loop after that initialize state s, and again another loop for each step of episode we have to repeat. Here initially what we used to do is we will take action A given by the policy pi for state s. Just take action A and observe the reward R and the next state s dash. Then the TD error del is reward plus gamma into v of s dash minus v of s. E of s also we are getting eligibility trace E of s is given that E of s plus 1. For all s, v of s is given that v of s plus alpha into whatever the del value we calculated above, and eligibility trace E of s we are including the updated value. Then E of s will become gamma lambda into E of s. Then new state s will become s dash until s is a terminal. The backward view of TD lambda is oriented backward in time. At the each moment we look at the current TD error and assign it backward to each period state according to the state's eligibility trace. At that time we might imagine ourselves riding along the stream of states, computing TD errors and shouting them back to the previous visited states, and as suggested. Where the TD errors and traces come together, each update depends on the current TD error combined with the traces of past events. In this diagram itself, we are looking back to the previous states and we are calculating the eligibility trace in the backward view. The better understand the backward view, consider what happens at various values lambda. If lambda is equal to 0, then by all traces are 0 at except for the trace corresponding to. Thus the TD lambda update reduces to simple TD rule which we henceforth call TD of 0 in the terms of the figure 7.8. TD of 0 is the case in which only the one state preceding the current state is changed by the TD error. For larger value of lambda, but still lambda is less than 1, more of preceding states are changed, but each more temporarily distant state is changed less because its eligibility trace is smaller. As suggested in the figure, we say that the earlier states are given less credit for the TD error. If TD equal to 1, then the credit given to the earlier states for falls only by gamma per step. This turns out to be just the right thing to do to achieve Monte Carlo behavior. For example, remember that the TD error del t includes the undiscounted term of in passing back steps. It needs to be discounted. Like any reward in a turn written by RT plus 1, which is just what the falling eligibility trace achieves. If gamma is equal to 1, lambda is equal to 1, then the eligibility trace do not decay to all with the time. In this case, the method behaves like a Monte Carlo method for undiscounted episodic task. If lambda is equal to 1, the algorithm is also known as TD of 1. Thank you.